Whoa. Look at this board. What? Hi, I'm Mr. G. We're at Bergen Community College, and I'm giving you an overview of spring semester 2018. If you're new or you're a veteran of the electric car building team, you're going to want to see this video. Check this out. Starting over here. Where's number one? Starting over here. This is the chassis. This is the chassis of the truck. What is a chassis? A chassis is just a ladder. And it's kind of like the word knife. There's parts that don't make sense. Okay, so it's chassis, not chassis, blah, blah, blah. All right? Now, why are we doing this? I'm going over, this is an overview of everything you would need to know to build an electric car. Overview. Okay, so here we go. We're going to take the car and we're going to knock it off the pedestal. Put it on the ground. All right? This is your chassis, right? Boom. Inside the chassis, this is your top view. There's an engine. The engine's connected to the transmission, which is connected to a U-joint, which is connected to a differential, which puts the power to the wheels. Okay, that's the top view. Why do we have a top view? Because that's the way engineers look at stuff. Orthographic, flat sides. The top, here's the side. Okay? That's number one. All right, number two. Is this number two? All right, so that we went over number two. Where's number three? Arm. The arm. Okay, so so here comes the question. If you got a gasoline piston engine and it's sitting inside the engine bay, right? And it's sitting inside the cradle of the chassis, which is a ladder basically. How do you hold the engine in place? And what you're going to do is you're going to put these in, which are basically the engine mounts. It connects the engine to the chassis through an arm and a piece of rubber, which is called a bushing. It's basically like hanging on like that, okay? It's like a mount. All right, so that's important to know, because if you change out the motor, if you take out the engine, is that going to fit still? If it will be a different size? No, it will not fit. So that's why we have to make custom motor mounts. So we're going to have to learn welding. All right? Okay. Now, moving on, I think to understand the importance of a transmission, because now the engine, it connects through this green line, it connects to the transmission. But what is a transmission, right? Like, what is that? Okay, a transmission is basically like bicycle gears. Okay? Your leg is pushing this up and down basically, and around. Your knee is going up and down, and then your foot goes roundy, and then what you do is you connect to the wheel, right? Now how does that work? So basically it goes through gears and a pulley. The pulley is basically the chain, right? So now if you have gears, that's part of a known system called simple machines, right? So simple machines are, in physics and science, there's a few of them. There's 7. So there's a screw, which basically is rotational. Well, let me just start by saying this. I know I'm going off on a side piece, but if you're going to work on electric cars, you got to know physics, you got to know science, but the big concepts, just to understand how things are made. Okay, so that's why we talk about simple machines. All right. Okay, here, come film this. I'm going to lecture like that, right? Okay, don't press this button. All right. Okay, cool. So the first one is the screw, right? Come on in. And the screw is basically when it changes rotational to directional. So it goes like this, and it goes in a direction. If you turn it the other way, it goes in the other direction. That's a screw. Very simple, right? A wedge is a knife, all right? And a knife splits stuff. That's a wedge, right? You can see me and the thing. Okay. An inclined plane, it's basically a hill. When you go this way, it rises you up. So it's like a hill. That's an inclined plane. A wheel and axle is a circle and a pin, right? A pulley is basically a rope that goes around a wheel. So you can pull on one side and the rope goes the other way. It's like changing the direction, right? Goes around and comes up. A lever is basically a long arm that's on a pivot. They call it a fulcrum. They like to be fancy. It's a pivot point. That's all it is. It's a center. If you put 1,000 pounds over here, at some point it'll feel like 100 pounds, depending on the distance. At some point it'll feel like 10 pounds, and at some point it'll be 1 pound. Now why is that? Because the longer you go, the easier it feels, because you're trading distance for input. Because you're going to have to travel further. So if you are putting the same input in, just over a longer distance. Okay? And then the last one here is gears. This is why I mentioned it, because of the bicycle. The gears are basically round levers. So if you have a gear like this with 8 teeth, okay, and you rotate once, and you're on a gear that has 4 teeth, it's going to rotate twice. That's called the gear ratio. Okay? This is the transmission. All right? Now, why do you need a transmission? Right? Think about it. If you're on a bicycle, right, there's a point where you're going so fast that you can't go any faster because your legs. So your legs are limited to a certain RPM, which is a rotation per minute, RPM, rotations per minute, right? Well, the engine has the same thing. So its range is about 1,000 to 7,000, depending on the car, right? So if that's the range, we know that just like a bicycle, you need more range, right? So that's why you change the gears. So when you start on a bicycle, you're going like this, then the bike goes fast, so then you can't keep up, so you change the gear. Now you're going slower, but you're going faster. And that's this. You changed the size of the gears. And basically on a bicycle, your chain is the pulley that connects the 2 gears, but it's basically gears, right? And that's why they call it simple machines, because when you connect them together, they are called compound machines. Compound machines are multiple systems. Where did I write that? I forgot. Multiple systems together.
Right there.
Where is it? Oh, here we go. A gear and a pulley together they call it compound machine. I call it multiple systems. All right, because everything, if you break it down, just like I said in the beginning, let's get off the pedestal. Let's break this down, right? And let's call it what it is. They're systems. We just bring them together. All right. So you have this transmission that allows for a larger range. Your RPM is times your circumference equals the circumference of the tire equals the RPM, the miles per gallon. I kind of breezed over that part because you basically understand it through a bicycle, right? You're pedaling really fast, then you got up to speed, and it's easy. You click, now you're going faster, but the pedals are going slower. Okay, we understand that part. So you're going to need the same thing for the engine, right? Okay, but before we even get there, let's back up a second. Let's break it off the pedestal. What is an engine? Is that the good part to get to now? What's an engine? I mean, literally, it's just a box with the word engine on it, right? No. Okay, so what's an engine? An engine, believe it or not, is basically just like a bicycle. Come on in close to the bicycle. Your knee goes up and down, and then your foot goes round and round. So what we do is, this is the engine. It's a piston with a connecting rod. This is your knee. This is your foot on a crankshaft that goes round. That's the pedal, right? So it goes round and round and round and round and round. But then, and it's up and down, turns into rotational. And I know you got to be thinking, if you're smart at all, you got to be thinking, well, what makes this go up and down? Because I know what makes me go up and down. I push it with my leg, right? But how does this happen? So that's a good question, right? So that leads us to this. Okay? The 4-stroke process. All right? Now what happens here? Let's get in close. Right? What happens here is you have a piston. When it moves down, it opens up a valve. Let's just trust me on opening the valve. It's an open shut, just like a faucet or a window. You're opening something, right? Open a valve, and it pulls in. It pulls in fire minus the spark. So you're like, what's fire minus the spark? Well, what's a fire? Let's start there. What's a fire, right? A fire is hydrocarbons. That's anything made by the sun. That's plants. Oil is dead plants. That's basically what you're pulling in, like a vapor of oil, which they call gasoline. It's a mixture of lightweight oil that turns into a vapor. Anyway, it's dead plants. Mix it with oxygen. 21% of air is oxygen. And those two, that's intake. Right? So let's go back over here. So you're pulling in the plant air. I'll call it plant air from now on, right? You pull in the plant air, then the next thing you do is you close it. And you have this area right here, you compress it. So the thing is like this. It's imagine if I open the door and I have about 100 people. Come on in. Come on in the room. No problem. Come on in. Come on. Yeah. Everybody grab a seat. And there's not enough seats, so you're gonna have to stand. And every person represents a piece of plant, a hydrocarbon, which is hydrogen and carbon together, right? Come on in. Come on in. Oh, another 100 people. Come on in. Come on in. I got 200 people in here, right? Okay, close the door. Now everybody's like, why are you closing the door? And I'm like, trust me. So I go over here and I create a wall. I take the wall and I move it towards you, right? Now I'm moving the wall, right? And everybody's like, whoa, it's getting kind of tight in here, right? And we're all getting tight. We're going into this corner over here and they're getting tight, just like here. Just like here. Getting it real tight in there, and everybody's kind of up against here, and they're like, they feel like they're on a subway car in New York City in the rush hour, and they're like, dude, this is really uncomfortable. And then just at that moment when I'm like, oh, you're the most uncomfortable, I can push you, and they're like, yeah. I take out a mouse and I throw the mouse in the crowd, and what happens? Oh my God, people are freaking out, and I can't hold the wall. They push the wall back, right? I can't hold the wall. Can't hold it. That's what happens here. The mouse, the reaction, the catalyst, the spark that makes everybody upset. That's this. The spark plug. That creates fire because the potential was there. People were already upset. Right? Boom! Pushes the piston down the wall. Cranks over the thing just like the pedals, just like here, creates rotational energy. So I just took in dead plants in a vapor form, mixed it with oxygen, compressed it, intake, compression, boom, combustion, explodes, and I use that explosion to push the wall, the piston. And by the way, it's similar to this. Get in close. It's just like a syringe. You're pushing something, a fluid. It could be air or it could be liquid, you know. And then the last part is, what do you have left after a fire? Smoke. I open the valve and I get rid of the smoke, and then we start again. Intake, compression, combustion, exhaust. That's how it happens. All right, so that is the 4-stroke process, and that is an engine. Whenever you hear V8, it just means that there's 4 cylinders on one side, 4 on another in a V configuration with 1 crankshaft down the middle. Different video, don't worry about it. Point is, that's what's inside there. Okay, so Now, where are we at? Let's see. Okay, so are we at electric motors now? Oh, okay. All right, so everything was fine using piston engines for years and years and years. I think Mercedes-Benz was the first one to put the piston engine on like a three-wheeled cart in like 1895 or something like. Yeah, I'm not exactly sure which one. And what they ended up doing was they ended up getting to market very quickly. But anyway, long story short, we've had like over 100 years of this engine. It's a great engine. There's a couple problems though, right? Let's go over the problems. Engine problems. The first problem everybody kind of knows about is the supply of the oil, right? That determines the price, that determines where you get it from, okay? The second problem is the smoke. Smoke has carbon in it, right? And what happens is, over the last 200 years, the carbon has risen dramatically compared to the carbon documents before that. That changes our atmosphere. And real quick, if you don't know anything about the environment, it's very simple. The more carbon in the air, the more the sun's energy gets trapped, which brings the temperature up on an average, which changes the weather and makes California drier and makes Florida have more storms. So there's fires and floods. So this is kind of like what's happening. Things are getting out of balance. The Earth is like a round object, so it's balanced. And when you change the way the balance is set up, then you change the environment. Okay. The third problem, and now let's say you don't care about this. You don't care about the supply. You don't care about what happens to the environment. That's no problem. I don't care what, this is just facts. But let's say you're like, oh, that's not real. Doesn't matter to me. Doesn't matter to me. What matters is the efficiency of the engine is only 20%. And the reason we know this is because when you walk up to an engine and what do you feel? It's hot, right? You're like, oh my God, the engine's hot. Well, that energy is lost. So every time you heat an engine, it's like a kettle. Look at this. When you put a fire underneath the water kettle, right? A lot of the energy goes away. That's loss. That's just engineering, okay? So there's only 20% efficiency, which translates into something everybody cares about, which is dollars, right? So you got yourself a situation where if you put $1 worth of fuel, you're only getting 20% energy out of it, right? Now, if you just do a quick Google search and look up the efficiency of, we'll get to that in a second, hold on. So you can look this up, it's around 20%, right? Okay. Now the fourth problem, and probably the most exciting problem, is the performance. Now, everybody has this dial in the car. It's like an RPM count, right? This is how fast your engine's spinning. When you start the engine, it's on 0, and then you get to like 1,000 RPM. It's like idling. It's like do 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 do, and then you start driving. But you know that you don't get 100% of your power until you hit what's called the power band. So between around 3,000 and 5,000 RPM, that's your sweet spot. That's where the most efficiency is. But before that, you have very low power, and at the top you have very low power, and it only goes to about 6,000 or 7,000 RPM. Okay. Now think about it like a tennis racket, right? If you have a tennis racket and you hit it right in the center, that thing sails and it's like you don't even feel it. Boom, right? But if you hit it off the end or you hit it very close, it doesn't go very far and it vibrates the handle. That's inefficient. You're getting a lot of feedback and you're putting energy in and you're not getting a lot of return. So that's what it is. It's basically like a sweet spot, right? So why is that a problem? Well, you have a problem with the supply, a problem with the carbon pollution. You have which sets the balance off. You have a problem with efficiency, which translates to dollar, and you have a problem with the power band. So, is there any way to solve this problem? Sure. Some engines are more efficient than others, but generally it's around there. So what we're going to do here at Bergen Community College is we're going to take the engine out. And we're going to replace it with something much more efficient, which is an electric motor. Now, the electric motor is around 75% efficiency, and I just looked that up. But if you think about it from a business standpoint, why is it that the trains are electric? If the piston engine was better, how come they don't use a piston engine on a freight train? It's just not powerful enough, and it's not efficient, which comes down to dollars. This is something you can't argue about, right? So, if we're going to switch it, let's talk about the advantages. Number one advantage, when you go from 0 RPM all the way up to like 10,000 RPM, you have 100% power. Whatever your rating was, the size of the motor or how much energy you're willing to put into it, whatever your rating, if it's 100 horsepower or 200 horsepower, whatever it was, you're getting all of it from 0 all the way up to the maximum RPM. That is a significant advantage, okay? Now, here's where the challenge is. If we're going to do this, we're going to make some changes. So the first change I talked about earlier, which is the engine mount, these are no longer going to fit. Now, how do I get the electric motor to hook up to the transmission? Now you're thinking, why do I need a transmission? Because the same problem with the bicycle. You need a range, okay? Even if we have more power available for longer, we still need a range. It's just like saying, well, I have a stronger person on the bicycle. You still need gears, okay? In some scenarios, you might not, but we're going to go with stock. And we're not going to change anything but what rotates the transmission. So we're keeping this build very simple, okay? Transmission, how do I get this electric motor that is different size? How do I get it onto here? Well, I have to have an adapter plate. That was the green line. That's a custom made thing. You can't go down to the adapter plate store and just buy one, right? The other thing is the coupler. How do you get the shaft to hook up with the transmission? We have to make one. So we're going to make it here at Bergen Community College. We have a machine shop, right? Okay, the other thing is, where are you going to put the batteries? Well, they used to put in the ladder, they used to put the gas tank, and then they had exhaust pipes. Those are gone. So we're going to put the batteries in a box, and we're going to connect those to a little computer. It's about this big, and that changes DC power to AC power. Is a whole other story, a whole other lesson. We'll get to that. But anyway, it's alternating current, and so that's going to move the electric motor. Now we're almost done, but the question is, someone might say, what's an electric motor? Like, why is it that if I add electricity, does it rotate? Here's why. An electric motor uses magnets, okay? So if you take a piece of steel, right, and I wrap it in wire, and I put a positive negative, it will pick up other pieces of steel, right? So I can just turn this magnet on and I can turn it off like a switch. Now if I could do that in a circle, if I could say here's a piece of steel and here's a magnet and I say on, then I say off and I say on, it'll rotate there and it'll go around. Now imagine it infinitely turning on and off in a circle. That's an electric motor. That's basically it. The only other thing I would add is that the only way for this to happen, the only way for someone to learn all this and deploy a good motor mount, to make an adapter plate, make a coupler, build a battery box, learn how to connect those with all the electric circuits, and do it in a way that it's safe and they feel comfortable. The only way to do that is through failure. Now you might be thinking, what's he talking about, right? What I'm talking about is, contrary to traditional school, where the failure is bad and good memory of what they told you is valued. What I value is the individual. I want you to try to make something, right? So you're going to try and make this. and you're going to see if it fits. You're going to build it out of cardboard. You're going to put it on SolidWorks, which is a computer program. You're going to see the shape. You're going to try. You're going to try and do this. You're going to try, and it's okay, right? And what failure proves is that you're an individual. Now, I know I went from engineering into philosophy or whatever, but I'm a teacher. So my job is to let you know that we are in an engineering environment which puts us in failure as the most valuable thing. Because if you fail in making something, then you learned how not to make it, and you'll learn another way, okay? The worst thing is quitting if you're trying to do this. If you look at something and say, oh, it's too hard, and you just walk away. Yeah, that's, to me, equal to failure on the school side of things. But Mr. G, I like to keep things closer to real life. I think that's it. Did I miss anything? That's it, right? All right, if you have questions about this, if you want to join our team, we need people. We need welders or people that want to learn how to weld. I don't mind if you try failing, right? We need people that know that want to run the wires, that connect this. If you don't know how to do it, we'll teach you, and I don't mind if you fail, right? We need people that want to learn how to break down the ideas, cut it off the pedestal. Don't put the car on the pedestal. Break it down into systems and understand all those systems. Last semester we did relays. We did electrical circuits. We've done SolidWorks, which is problem solving with shapes on a computer. We've done soldering. What else did we do? That's basically it, right? All right, so so this is for current team members, but also people that want to join the thing. This is Bergen Community College. We're here in Paramus, New Jersey. I'm Mr. G. Thank you for watching. If you got any comments, love to hear them. That's basically it. Anything else? All right, I'm Mr. G, Bergen Community College. See you later.